There we go. Thank you all so much. It's really an honor to be invited to speak at this symposium. And I'm going to tell a little bit of a story. And that is that I'm at Princeton University, and I been there about 3 years. And so when I interviewed at Princeton, I think it was my second interview, Chris and Elena dropped everything, spent a morning with me, took me to lunch. We talked in depth about a bunch of research ideas, which was really touching and a big part of, my understanding just how important the GFDL Princeton connection is, and it was a real appeal to draw me to Princeton, and during the course of that conversation, those conversations, Chris said, well, so are you thinking about putting power flow in, GFDL climate model, or connecting it with a land model, or some kind of, large scale groundwater? That kind of stuck. And where that stuck in a way was the impetus for this project that we have called hydrogen. I'm going to tell a little story about hydrogen and talk about kind of what it is and how it's evolved, and then maybe kind of where it's going to come back around to that little seed, as Nate said, that Chris planted. So hydrogen is this it's a National Science Foundation Convergence Accelerator project, which is a new project with a new category of thing within the National Science Foundation. They have a phase 1, phase 2. It's this whole crazy thing. And what we've developed is a machine learning platform for hydrologic scenario generation. And I'm just showing kind of the faces of the team because I'm going to highlight some of their work. Laura Condon at University of Arizona is the PI, and Peter Melchior, who's an astrophysics at Princeton, is actually a close collaborator with us, along with Andrew Huang, Elena, and Yuling. So the whole idea behind the impetus for why we need this is, of course, Lake Mead, largest surface water reservoir in the US, is running dry, right? And we've all seen the headlines, and this change is humongous, right? So we can see this from space. There's a lot of these different visualizations, right? So this is 2000, last time it was full. This is currently where it's sitting, roughly in the 30-ish%. And to just sort of bring back a lot of Chris's greatest hits, the current drought, as Dennis said, is driven more by rising temperatures than lack of precipitation, right? So the Million Done Science 2020 paper was a huge influence in why we should think about this system a little bit different than we have. Think about droughts different than we have, when precipitation remains constant, temperatures increasing. And the big piece that we really grabbed onto in talking with water managers and others is that the past doesn't represent the future, right? We call this no analog future. We have no analogs to draw from. And we have a quote that we used in the pitch and a bunch of different things in this from Ted Cook, the general manager of the CAP. And this no analog future becomes really important because, of course, this is the whole point of stationary is dead, right? With water management, we don't, our past statistics that we've, had all of these sort of empirically based in the West. What is the April 1 SWE, and how is that related to the amount of flow into reservoirs in, say, September at the end of the summer? These are all broken, and these are all not working anymore. And so that was kind of the big piece. Obviously, a big part of influence from Chris's career that we took and that we kind of ran with. And what's important, and I'm highlighting some of Laura's work here, is that we have these big integrated models that are non-stationary, that do some really interesting things. And this is some work that Laura did in Nature Communications that I'm not showing the slide that's maybe relevant to one of the other Chris's papers that was mentioned earlier, but really thinking about, as you increase temperature, you increase potential evaporation, but you certainly don't increase actual evaporation. That depends entirely on land surface processes, plant processes, water availability, convergent flow, and the response of groundwater, of course, is nonlinear to this. And so this is another one of these big themes that Chris has set out, many times over. Now, these integrated models are really great tools, and sort of this idea that Chris, planted at lunch that one day was, well, let's explore this, but they're super, super, super expensive to run, right? They are, really large scale supercomputer type simulations, because we're rigorously solving coupled nonlinear partial differential equations for nonlinear Richards equation for the subsurface everywhere, and shallow water equations. So in comes machine learning. And so I use this a lot. These are two images of water table depth. This is the Taylor Park, Upper Taylor, and the Upper Colorado River. And you can't tell which is an AI and which is par flow. One is, trust me, one is an AI, one is par flow, and they're indistinguishable, right? And statistically, they're indistinguishable as well. And so some of the work that we did and some of the things that we, kind of advanced to sort of get to this point, we're using sort of what we call physics-informed ML. So we build these super fast emulator models of par flow. We have a bunch of papers on this. I'm going to highlight first Huang's work. And the idea here is you build a full-blown emulator of the entire par flow model. So you get overland flow, you get storage, you get, and we demonstrated this in 2 different subwatersheds. And then you can also do this to try to predict future change, this was some of Elena's work. This was published just pretty recently in 2022. And the idea here is that you can, machine learning emulators, machine learning models are really good interpolators. They're bad extrapolators. If the data isn't reflecting the future change, which then the machine learning emulator trained on that data doesn't do super well in realms that it hasn't seen. And that gets back to the wither water management stationary is dead again, right? So the idea is that we can then impart with the physically based model these futures and training data that are synthetic, but that represent future change in a way that now the MLs are interpolating again. So we've built the simulator, we've done all these things, we can train, we have an app that we can run on demand. And all of this is sort of at the, kind of the peak of the project. You can go in, log in, you can click on any watershed, you can, crank through any kinds of data. It's all sort of pulled together on a Princeton data server. And then you can run these automatic forecasts. So you can run these 3-month forecasts with the idea, this is the pretty much the entire Gunnison. And the idea here is that these run in seconds, almost in real time. You can run, effectively an emulator of a par flow model instead of running on a supercomputer and massively parallel. These things run very fast, and fast enough to run ensemble forecasts, fast enough to run, sort of on demand. And so this is one ensemble realization for a 3-month scenario forecast based on the CPC, running from today forward. And all of this is, running as a service. So it's, we've sort of accomplished a ton. And now we're thinking about, well, what does that mean in terms of the entire CONUS? And so this is Andrew Bennett, who's a postdoc with Laura and some of his work. And he has been running over the entire CONUS. And this is just 2 snapshots, and you can't, obviously you can't dive in and look at the differences in the 2 simulations. But trust me that they're quite similar, except one is, a par flow run that ran on a supercomputer, and the other is same output, but it runs on 1 GPU in 6 minutes. So we're talking thousands of times faster. And we can also combine data-driven approaches. This is really new work by Yu Ling, that just are purely data-driven approaches for coming up with kind of the current state of our water table depth, which, as Elena mentioned, is really important for our spin up and initialization. Groundwater takes forever to spin up. And having some other ways to sort of initialize these models becomes really useful. So let's wrap this back around. So what's our path forward? Well, in the Convergence Accelerator, actually, one of our partners was GFDL on the land modeling group. And at the time, we had a lot of these great ideas, we had a lot of great discussions, but we weren't really ready for prime time. We didn't have the machinery built. We weren't really ready to sort of scale out these ML emulators to the full continent. But we are now. And I think this idea that, that Chris, the seed that Chris planted at lunch several years ago, and then, kind of feeding on some of the groundwork that his amazing papers have laid, we're now at the point where we have these rapid approaches that run thousands of times faster than the integrated model, and we can do high resolution groundwater simulations now at global scales, modern hardware, in a way that we can kind of drop these in or connect these into land model type simulations. And then we can also do, kind of multi-scale things and tie in with what Nate was talking about in terms of hydroblocks and a lot of the subgrid variability. So just going to end there and thank everybody for the opportunity to talk today. And of course, thank you, Chris, for inspiring so many things throughout my career. And there was the band name, Wither Water Management, or Stationary Is Dead, I can't remember, mentioned earlier. And in a lot of ways, Chris's papers are sort of like these big albums that came out, right? So depending on your generation, either Sgt. Pepper by the Beatles, or Nevermind by Nirvana, or OK Computer by Radiohead, or I'm sure others that I'm now too old to use as a reference. And when the Wither Water Management paper came out, literally, Stefan Collette, who I have worked with a ton over my career, literally ran to my office at Livermore. We were down the hall from each other. They literally ran to my office like, "Did you see this paper? Did you see this paper? We have, like, this is amazing. This is exactly what I've been thinking about. There's so many things that we can do that, like, and it was like one of these, was like a new record that just came out that, like, you listen to fully and it blew your mind. It was that same sort of energy around, wow, like, look, these ideas that we've been thinking, somebody really verbalized them in a way that just clicked and made so much sense. And one of the papers that Stefan and I did soon after that, really rapidly after that, it was like this really inspiring thing, was completely inspired by this idea of non-stationarity in water models. And so thanks, Chris, and thanks, Kirsten, for the invitation, and really appreciate all the talks and all the great contributions.
Hey, Reed, thanks for coming. Thanks for your contribution. Thanks for your kind words. Yeah, you know what? It's getting late in the day. I need my coffee.
That's totally okay.
I'm blacking out. So you came to Princeton. We didn't overlap very long. We didn't have the opportunity to really work together on anything. But I look forward. I mean, the stuff you're doing is kind of blows me away, and it's almost hard for me to comment on some of it. But I really look forward to seeing where it goes, because I do intend to still be looking at the literature for another decade or two. So, good luck with all of that, and thanks for being here.
Yeah, well, thank you so much for your kind words, and absolutely best of luck. And anytime, as Elena said, we can get you to come back, we'll bring you back in.